Hi everyone, welcome to today's lesson. Today we're going to be working with implicit differentiation. And where I want to start with this implicit differentiation is going to be how we want to work with implicit differentiation, and more specifically, why we want to work with implicit differentiation. So far, we've known how to take derivatives for functions. Okay, so as we've been working with the previous sections or with the previous chapters, we've been building this whole concept of taking a derivative for a function. What we want to do now is we want to extract, can we take a derivative without actually solving for a function? In order to illustrate this, I have the equation of a circle here, centered at 0, 0, with radius 5. This equation is x squared plus y squared is equal to 25. So what's going to happen here is that what I want to do is I want to solve for y first. So if we solve for y, then what's going to happen here is that we're going to be left with 25 minus x squared. Taking the square root will then give us the plus or minus square root of 25 minus x squared. Now, this particular form here is a function now. However, this has two different components, or two different pieces. We now are splitting this function, or this equation, this circle, into two different portions. One of the pieces is going to be where the y values are positive, and the other piece is going to be where the y values are negative. In that particular instance, I'm going to illustrate that here, where we have a top half of a circle, which will be y is equal to the square root of 25 minus x squared. And we're also going to have a bottom half, which is y is equal to the negative square root of 25 minus x squared. Okay, perfect. And so again, what I'm doing on this circle, it's a little bit too dark there. On this circle, the bottom half is going to be represented by this. The top half then be represented by this. And again, now we have a function, or now we have two different functions. So the reasoning behind this is that we wanted to break this apart so that we can get two different functions. And once we have these two different functions, then we can go through the whole process of taking this derivative. So using the top half, I'm going to keep taking that derivative. Alright, so this is now going to get me y prime for this top half. Oops, excuse me there. Y prime. Once everything is simplified, I should be able to extract that y prime is x divided by the square root of 25 minus x squared. Now, that's pretty awesome there. So we're left with this. And what we want to do at this point in time is we want to interpret what we're looking at. And what it is that we're looking at is, oops, excuse me here, I forgot a negative. My apologies. What we're looking at here is that the denominator here, square root of 25 minus x squared, we can actually see that right here at the top half. Which means by substitution, this y prime turns into negative x divided by, this is y. Okay, well, let's look at the let's look at the bottom half derivative. The bottom half derivative, here is going to be x divided by the square root of 25 minus x squared. Well, that's really nice. However, we see the bottom half here again, and this bottom half kind of looks like the top half. The only problem is that there's a negative out in the front of that bottom half. But that's completely fine, because if we multiply the negative onto both sides, we get that the square root of 25 minus x squared is going to equal to negative y. Therefore, using that substitution, I'm still able to get this, that y prime is going to be equal to x divided by negative y. But hold on a second. Aren't these two the same? They're both the same derivative, which means that y prime doesn't matter what way we split or what way we decompose this function. Y prime turns out to be the same considering the initial function that we were working with. And this is where we start working with this whole implicit differentiation process. So we can go back just a little bit more and we can say, okay, well, how did we arrive here? Well, working backwards, let's see, I want to multiply both sides by that y portion. So we get y times y prime is equal to x. Okay, that's looking interesting. Well, we have an x squared here, and then we have a y squared in our equation as well. And so what ended up taking place here is that we ended up taking the derivative here. All right, but in that whole process, we had to have taken the derivative for y. Now, we're going to keep that in mind. And so to illustrate this, we're going to keep going and we're going to say, well, we don't necessarily need to solve for y in order to get this particular, let's say, derivative. So what I want to do at this time is I want to start with my function, or sorry, with my equation that x squared plus y squared is equal to 25. And in this case, I'm going to take the derivative with respect to x for both sides. Again, this all looks very, very familiar, or it should look very, very familiar. Taking that derivative now, well, I'm going to distribute that derivative into each component. The right-hand side of that equation turns to 0 because the derivative of a constant with respect to x is equal to 0. Awesome. Now, taking the derivative of the first term with respect to x, that's kind of nice. That just turns into 2x. But it's a second derivative, or the second term for this derivative that we have an issue with. The issue being that we now are taking a derivative with respect to x. However, we have a function y. Now, the function y is actually has an x embedded inside of it, which means when we take this derivative with respect to x for this y squared function, we must account for the derivative of x by applying the chain rule. The chain rule says when you take the derivative with respect to x, what you're going to do is you're going to differentiate the outer function, which means we drop the exponent forward and we get 2y, and then we multiply by the derivative of the inside function. The inside function in this particular case is my y function, which means I'm going to multiply by y prime. All of this is equal to 0. So if we go through and if we solve for if we solve for y prime, here we get negative x divided by y. And again, we got the exact same answer as we did at the very beginning. So as it stands, we don't need to solve for y in order to take a derivative. All we need to do is we need to make sure that when we take the derivative implicitly, that we apply the chain rule to any function that has the variable embedded inside of it in which we are taking the derivative with respect to. So that is something to keep in mind. And again, what I'm outlining here on your screen is that we used the chain rule. And all of our derivative properties will still apply. The chain rule, the product rule, the quotient rule, so on and so forth. All of that will still apply. And so we have to keep that in mind. And I'm going to illustrate that in just a bit. All right, so on the right-hand side of your screen, if we consider the function x times f of x, then what we can do when we take that derivative for this x times f of x is going to be that we need to use the product rule. And so here I'm just outlining that I want to use that product rule. And we're going to use the product rule because we have those two different components, or those two different functions. One is x and the other one is f of x. Now, because we don't know what f of x is, we just need to account for what its derivative will be. So when we use the product rule, we're going to take the derivative of the first function, multiply it by the second function, add it to the first function, multiplied by the derivative of the second function. Okay, so what does this simplify to be then? Well, this then simplifies derivative of x with respect to x is just 1. So this is just 1 times f of x plus x times f prime of x. And this is that chain rule process that we were talking about. Oops, I put f prime of y. I meant f prime of x. There we are. Now, what if we, notation-wise, change f of x? So what if we instead consider y is equal to f of x? Well, then revisiting our whole process up here, this is still going to stand as now x times y. Taking the derivative, it's still the exact same process. So applying the exact same process, we're still going to be left with 1 multiplied by f of x, where in this case f of x is y, plus x times f prime of x. In this case, it's going to be times y prime. And in this particular instance, we must always account for y prime. And this is how we then start viewing that we are using the product rule when we're using implicit differentiation, if we ever have our x variables multiplying by some y function. And we must always account for this. Now, we can always account for the product rule, we can always account for the quotient rule, the power rule, and the chain rule, and we must always apply them. So let's start off with some examples. On this example, I want to say find y prime where 2x squared plus xy minus y squared is equal to 2. And again, we're going to take it step by step. Well, what are we going to do? We're going to apply the derivative. If we want to find y prime, what I'm going to denote here, and I'm just going to write a note, that y prime is this dy dx. So when I'm trying to find the derivative, or when I'm trying to find y prime, that means that I'm going to have to take the derivative with respect to x for both sides of the equation. Is equal to 2. Oh, sorry. d dx of 2. As such. And then we're going to go through, and on the left-hand side of the equation, again, we're going to go through and we're going to make sure that we take the derivative of each individual term. And the reason I'm doing this, showing why we need to take the derivative for each individual term, is because we're going to need to apply either the chain rule or the product rule as we take those derivatives. Now, on the right-hand side of the equation, the derivative of the constant with respect to x will be 0. So the first term, when I take that derivative, well, with respect to x, that's going to be 4x. That's nice. The second term, I need to use the product rule. Why do I need to use the product rule? Well, because I have the function x and then the function y multiplying one another, and y has an embedded value of x. So in here we need to use a product rule, which will be the derivative of the first function. So the derivative with respect to x of the first function x multiplied by the second function y plus the first function x multiplied by the derivative of the second function, which is y. And I'll highlight this to say that this is the derivative that uses a product rule. Awesome. Last term, minus, I now need to take the derivative with respect to x for y squared. Now, in this particular case, since y is a function of x, when we take the derivative, not only do we need to account for the the power rule, we also need to account for the chain rule. So we're going to drop the exponent forward. So we drop the exponent forward, so we get 2y multiplied by the derivative of the inside. And the derivative of inside is just going to be the derivative of the function for y. So again, we use the power and the chain rule there. And I'm going to highlight that. And again, this was the power and chain rule. So now we can go through and we can simplify a whole bunch of terms. Well, the first term is just 4x. The second term now becomes just y. The next term now just becomes x times y prime. And the last term then becomes 2y multiplied by y prime. And this is equal to 0. Awesome. And so again, just highlighting the pieces as to where they belong. There we are. Great so far. Now, if we want to solve for y prime, then all we have to do is isolate y prime. So the way we're going to isolate y prime, anything that does not have a prime for my y values will then get moved to the other side. So we get minus 4x minus y. Factor out that y prime. Looking good. And now all we get to do is divide by x minus 2y. So what we get here is that the derivative y prime now gets us 4x minus y, all divided by x minus 2y. And again, notice, we didn't even solve for y. There was no need to solve for y. We don't need to know what the function is. As long as we can take implicit derivatives, everything's going to work out just fine as long as we always stick to the differentiation rules that we learned previously. That's amazing. So I hope this makes derivatives a little bit easier moving forward. And again, we're going to investigate seeing if it does or doesn't, and we're going to keep using these techniques. So let's keep going. In this example, again, I want to find dy dx where excuse me. y to the fifth plus x squared y cubed is equal to 1 plus x to the fourth times y. There we are. So again, we're not solving for y here, but we can still find y prime. Let's go through that process. All right, so let's take this derivative. So again, I'm using the notation to write out the derivative with respect to x. And again, when we apply the derivative, we must apply the derivative onto both sides of this equation that is given to us. And in doing so, we can now go through the whole process. Derivative with respect to x for y to the fifth. We're also going to do the derivative with respect to x for x squared y cubed. And we're also going to do the derivative on the right-hand side for 1 with respect to x, and then the derivative with respect to x for x to the fourth times y. Now, the first derivative, this is a function of y, this is a function represented by y that has an x value embedded inside of it, which means when we take the derivative with respect to x, we have to apply the chain rule. Drop the exponent forward, subtract 1 from the exponent, multiply by the derivative of the inside. In other words, y prime. So this in here was the chain rule that we're using. And I'm going to highlight this just again to signify that we were using the chain rule. Perfect. There we are. The second one, the second term, what's going to happen here is we're going to take the derivative. However, what's going to happen here is that we're going to need to apply the product rule. In applying the product rule, we're going to take the derivative of the first function. So the derivative of the first function multiplied by the second function plus the second function multiplied by the derivative of the first function. Derivative of the first function. I keep saying the same thing. Derivative of the second function multiplied by the first function. There we go. And so again, this was the product rule. Nice. There we go. Now let's focus on the right-hand side. On the right-hand side, we're now going to take the derivative of 1 with respect to x. Well, that's naturally going to be 0 because there's no x values embedded there. Now we need the product rule once again because now we have x to the fourth times y. So applying the product rule once again, we're going to go through and we're going to say we're going to take the derivative with respect to x for x to the fourth, multiply by the second function, which is y, plus the first function, x to the fourth, multiplied by the derivative with respect to x for the second function, y. And again, this here is another product rule. All right. So again, product rule once again. Perfect. So let's go through and let's simplify wherever we can. For the first term, can't simplify any further. We're left with 5y to the fourth multiplied by y prime. Second term, this can get simplified because now we can apply the derivative, which means we're going to be left with 2x multiplied by y cubed. The third term, we can simplify. We're going to be left with x squared multiplied by, let's apply the power rule, 3y squared multiplied by y prime, because of the chain rule, is equal to, well, that's 0, so that doesn't do anything. Derivative of x to the fourth, this is now going to be 4x cubed multiplied by y, plus x to the fourth multiplied by the derivative of y with respect to x, in other words, y prime. And so again, we did need the chain rule, or chain and product rule, and that chain and product rule came in when we were looking at this specific term. And let me highlight this here. There we are. There we go. Looking good so far. Let's keep going. If I want to solve for y prime, that means I need to isolate y prime. So let's make sure we get y prime by itself. 5y to the fourth multiplied by y prime, plus, this is going to be 3x squared, y squared multiplied by y prime. Move this over to the left side, minus x to the fourth, y prime, is equal to the right-hand side, which will now be 4x cubed y, and then I am going to subtract this term that I haven't really touched on the left-hand side, subtract it over to the other side, which will be 2x y cubed. There we are. Now, from the left-hand side, all of those components now have a y prime, which means we can factor out a y prime, and we're left with 5y to the fourth plus 3x squared y squared minus x to the fourth. The right-hand side still stays exactly the same. And in order to solve for y prime, we're going to divide both sides by that component, which means y prime is going to equal, let's get a good fraction bar here, all right, here we go. So y prime is equal to 4x cubed times y minus 2xy cubed divided by 5y to the fourth plus 3x squared y squared minus x to the fourth. Look at that. Isn't that amazing? That looks great. Awesome. Now, we're going to do one more example. And the example that we're going to do is going to look somewhat nice, at least in my opinion. Oops, excuse me here. I just want to make sure I box my answer. There we are. Okay, so for my last one, for my last example, we're going to go ahead here and we're going to find y double prime, where we have x cubed minus y cubed is equal to 7. That looks good. So let's go through and let's find this derivative. All right, so let's apply the derivative here. We want to find y prime first. So let's go with y prime. And again, we're going to do this implicitly. So finding the derivative with respect to x. What's going to happen here is on the left-hand side, we're going to be left with 3x squared minus 3y squared multiplied by y prime. Again, that derivative accounting, or sorry, that chain rule for derivatives, making sure we account for that. And if we solve here for y prime, then what we're going to get is that y prime will be equal to, let's see, move that over to the left, to the right side, that's going to be negative 3x squared. Negatives will cancel, 3's will cancel, and we're going to be left with x squared over y squared. And this is our y prime. So that looks really good. Now what we have to do is we now have to take the second derivative for this. That means that we're going to apply our derivative once again, but this time we're going to apply the derivative to the right-hand side, where the right-hand side is a rational function. In this particular case, we're going to have to use the quotient rule. On the left-hand side, we just get the same derivative once again, so that's going to be the second derivative, so that's y double prime. On the right-hand side, we need to use that quotient rule. So that's going to be the derivative of the top, so d dx for this x squared, multiplied by the bottom function, minus the top function, multiplied by the derivative of the bottom function. All divided by, oops, whoa, hey, this computer's going all crazy here. There we are. All right, so where was I? There we go. I was drawing a division bar. There we are. Divided by the bottom function squared. So that's y squared squared. Perfect. And I'm going to highlight this just to denote that we are using the chain rule here. Let's go with this color. Or sorry, that we are using the quotient rule. All right. There we go. Perfect. Let's keep going. Y double prime, derivative of the first function, that's 2x. And you know what? Let me get a good fraction bar going here. All right, derivative of the first function, that's going to be 2x multiplied by y squared minus, for this function, drop the exponent forward, we're going to be left with 2x squared multiplied by y once we subtract the exponent by 1, and then multiplied by the derivative of the inside, so we still need to multiply by y prime. There we are. All of this is going to be divided by y to the fourth. Looking good. Wow. Now we're almost done here. The only thing that's really different here is that we have a y prime embedded in this second derivative. In other words, we have a first derivative embedded inside of the second derivative. If we can try to eliminate that, let's do so. So on here I'm just going to say try to eliminate y prime, or substitute. And so what we're going to do is, we know what y prime is. Y prime is this x squared over y squared. And that's where I'm going to make my substitution. I'm actually going to go through on the top part of the screen up here, and I'm going to make that substitution to say that y double prime is equal to, let's get my fraction bar once again. Oh geez, here we go. And this numerator will be 2x multiplied by y squared minus 2x squared multiplied by y prime. And again, we know y prime to be x squared over y squared. All of this is divided by y to the fourth. So how do we simplify this? Well, what I'm going to do is I'm going to multiply both of the equations, both top and bottom, just by y. Multiply this by y, multiply this by y. In this instance, we now get this fraction for my second derivative to simplify just a little bit more. Distribute the y, that now becomes 2xy cubed minus this y, 2x squared y, will cancel out with one of the y's in the denominator for that y squared, but then the other y is going to fully cancel that out, which means we're going to be left with x to the fourth. So that's going to be 2x to the fourth. Okay, it's not looking too bad. Divided by y to the fifth. Remember, like I always say, if you can factor, go ahead and do so. Factoring is your best friend. So let's factor numerator. I see a 2x that I can factor, which means I'm going to be left with y cubed minus x cubed, all divided by y to the fifth. And hey, wait a minute. This in the parenthesis, that looks oddly familiar. Isn't that the initial equation that we started with? Except if we multiply by negative, we actually get y cubed minus x cubed, which means that y cubed minus x cubed is actually negative 7. So this then becomes 2x multiplied by negative 7, all divided by y to the fifth. Check that out. That is awesome. Simplifying this, y double prime now becomes negative 14x divided by y to the fifth. And our second derivative no longer depends on the first derivative. That is where we want to be. So remember, moral of the story, if you can simplify, simplify by factoring. If you can make a substitution by identifying the original function that you were given, go ahead and do so. I guarantee that it will simplify to something real nice. So I hope that you all enjoyed this lesson, and if you stick around, we're going to be covering rates of change that is going to be using these derivatives. So I will see you all then.